you will get
0.93
I'm sorry?
0.93.
Okay. 0.09, you mean?
Yeah.
Okay.
1 meters, right? And that's about 9.1 centimeters. About 9.1 centimeters. And it's approximately 3.5 inches. Pretty, yeah, pretty big. Yeah. Yeah.
Could you like raise the board up?
Yeah, of course.
There we go.
Yeah. Yeah.
Would the expansion just be on the x-axis per se, or since it's like a pipe, would it also expand upwards?
Yeah, so since a pipe is usually characterized by its length, that's where you see the 9.1 centimeter, the appreciable. But yeah, it also expands this way also, yes, yeah. But since the diameter is probably not that much,
It won't go.
it's not that much, yeah, it will not be that much. But definitely, yeah, it will get larger. And we'll do the volume expansion now. Yeah, we'll do that. Yeah. So, let's get to the coefficient of volume expansion. So let's say you fill up your gas tank, right, in your car, and you put 15 gallons, and it's full. And so if it's cool in the morning, if it's hot during the day, the gas will expand. The question is by how much will it expand? And they have here different volume coefficients of volume expansion now. So let's do that. So the volume expansion. Very similar. The change in volume. So here is a volume. If the volume is this much, and then you heat it, let's say you have a sphere or something, the volume it will get larger. It will get larger. And how much is the change in volume? Well, you got the material itself, the thing with the material. It's called beta in this case, the coefficient of volume expansion. The coefficient of volume expansion times the original volume times the change in temperature. Okay, the coefficient. So this one is the coefficient. Coefficient of volume expansion. Yeah. Yeah.
Would the diameter of the inside shrink or change shape at all? Get larger or smaller?
So this is a solid volume.
Oh, okay.
It's like full, right? It's not the maybe my picture implied. So there is so let's say your gas tank here, and so there is gasoline everywhere, right? Yeah. So when you heat it, it will expand. The whole thing will expand.
Got you.
Yeah. The whole thing will expand. And it will expand by this much. So now how is beta related to alpha? Right? Yeah.
Delta T, right?
They are, yeah, delta T. Like beta and alpha? So let's see how it's related. It turns out that beta is 3 times alpha, approximately 3 times alpha. And here's why. I'll show you. So let's say you have just consider a cube. The book does it in differentials, but I will just do it this way. So here's a cube. And so the original volume of the cube, let's say, is L. It's L by L by L. So it's L this way, and L this way, right? So what's the original volume? It's L cubed, right? So now let's say I heat it. If I heat it, it will expand. It will expand in this direction, in this direction, and in this direction, right? In every direction. So it will become, sorry for my, so it will expand a little bit in every direction. And then, sorry. How do you draw something like this? So in every direction will increase by a delta L, right? Every direction will increase by a delta L. Because we said, here, from the coefficient of linear expansion, in every direction will expand by a delta L. So, what was I going to say? Yeah, so how do I get the expansion? So first of all, this is the original volume. Let me call it V0, the initial volume. The final volume, V final, will equal to, each side will expand by a delta L, right? It's L plus a delta L to the power 3, right? That's the new volume. So let's expand this. Square or cube it. What do you get? You get L cubed, right? Plus what? 3 L squared delta L? Yeah. Plus what? 3 L delta L squared plus what? Delta L cubed, yeah. Delta L cubed, right? That's how you expand a cubic. I think that's how.
Yeah, it's probably.
It is correct. It is correct. Yeah. It has to be symmetric. A 3 here, 3 here. Yeah. So now let's see what the change in volume is. Right? What the change in volume means: the final volume minus the initial volume. Right? The change in volume, delta V, will be the final volume minus the initial volume. So the final volume has an L cubed. It's L cubed plus 3L squared delta this, right? Subtract from it L cubed. What do you end up with? You end up with 3L squared delta L plus 3L delta L squared plus delta L cubed, right? I'm going to throw away this term and this term. We'll just throw them away. Why?
Because they're very negligible.
They're very small. See, this one, let's say you have a small number by itself. It's small, but then take that small number and then square it. Say it's 0.1 and you square it. What do you get? 0.01. So compared to 0.1, 0.01 is smaller, right? 10 times smaller. And this one is even smaller. If you do 0.1 cubed, you get 0.001. So this one is negligible, and this one is definitely even more negligible. So just throw them away. So we're approximating here. So the change in volume is 3L squared delta L. That's the change in volume, right? Yeah. So you have this. Delta V is approximately 3L squared delta L. Yeah. So now we want to relate alpha to beta. So delta V is beta V delta T, right? So this one is beta V delta T equals 3L squared delta L. Delta L is alpha L delta T. Okay, so what cancels? So first of all, here beta. What was the original volume?
L cubed.
L cubed, yeah. L cubed. Delta T. And then here 3. L squared times L is L cubed. And then alpha times delta T, right? So L cubed goes away, and delta T goes away. And you end up with beta is approximately 3 times alpha. So, anyways. Okay, and you can have a lot of these questions where you got 2 pipes and they are maybe at different temperatures, and they're made from different materials. At what temperature do they have the same length? And you have to set up an equation. They have different alphas. Or you can have an example like this. Let's say I have a pipe of this length. Let's say it's made of steel, and another pipe made of copper, and it's of this length, right? And there is a gap between them, and they're, let's say, 10 degrees Celsius. To how many degrees should I heat the whole thing so that the gap here becomes 0? The gap will close. So there are different questions that you can have. Yeah. Let's see. Good. We still have 15 minutes. I want to get to I was just mentioned these phases or phase changes. It's called it's different phases, like the different solid, liquid, gas. Each of them is called a phase. P-H-A-S-E, not a face. F-A-C-E. So phase. So if you go from solid to liquid, it's called what? You melt, right? Melting. And if you go from liquid to solid, it's called freezing. If you go from liquid to gas, or boiling. And if you go from gas to liquid, condensate. Yeah, you condense. Yeah. Yeah. So I just wanted to mention them. That's I mean, there is not much consequence to them. There is the triple point of water where basically all the phases kind of coexist, and it happens at almost 0 degrees Celsius, 0.01 degrees Celsius, and at a pressure of 0.006 atmospheres. Yeah, you can have all three phases. Yeah.
Oh yeah, I don't know if this is correct, but is plasma considered like a state of matter?
Plasma is basically, you boil all the atoms in there by themselves, and so it's, I guess you can consider it as a gas probably. Yeah, or maybe it's a different state. I don't know. Yeah. Yeah. So let's see here. Yeah. So phases. It was just more for completeness. And then you have like the phase diagram where it shows you at what pressure and temperature you should have what. Let's see. Now the ideal gas law. This is basically what we're going to work with. The ideal gas law. So the ideal gas law relates the pressure, the temperature, and the volume together, and the number of moles of a gas. So it's called an ideal gas basically because the atoms do not interact with each other. Real gases, the atoms do interact with each other, but they come close. So we're going to treat them, even if you have a real gas, we're going to treat it as ideal. Yeah. Why? Because it's simpler, makes life easier. So you can have atoms, and the gas could consist of monatomic gas atoms, a monatomic gas, meaning each unit is just one atom. Or you can have a molecule, basically a diatomic gas like oxygen, right? O2, or nitrogen, N2. So you hear the term monatomic or diatomic. That's pretty much what we deal with, monatomic, diatomic. The difference, diatomic, they could vibrate because they're bonded together, and it could rotate, which would result in different energy levels, which we'll talk about in the next chapter. Yeah, so what's the ideal gas law and how does it work? Let's erase. Big eraser. Gas law. It relates pressure to temperature and volume and so on. So, if you have a gas, here is a gas, and you put it inside a cylinder, you have to close the cylinder, right? So you close the cylinder. So basically, maybe the cylinder looks like this. So now you got your gas atoms here, and they're going everywhere, every direction, and they're bouncing off. And we will see next chapter that the pressure comes because the gas molecules, they hit the container, and every time they hit and bounce back. Remember, a force would be the change in momentum over time, right? Every time they hit and bounce back, that's a change in momentum, and they deliver a small amount to the wall. I mean, if you had only one gas molecule in there, that's hardly, you cannot speak of pressure, because you got one pressure at one point, it's delivering force, but then there is nothing for a while. But if you have an Avogadro's number, 10 to the 23, they're consistently hitting the wall, and you have a steady pressure. Okay? Steady pressure. So now what's the pressure in the gas? How can I figure it out? Suppose this piston here, let's say it doesn't have any mass, it's very light, it doesn't have any mass. There is only the atmospheric pressure from the top, right? So if it's in equilibrium, the reason the piston is in equilibrium is the force from the gas that's pushing it up versus the force from the atmosphere pushing it down. They're equal to each other, and so it's the same pressure as the atmosphere. If I want to make the pressure larger, I can put some weights here. So if I put some weights here, what happens to the piston? It goes down, yeah, it goes down. So if when the piston goes down, what happens to the volume? The volume decreases, and what happens to the pressure? Yeah, the pressure goes up. And so that you do all these experiments, and then you can, let's say, if you want to keep the temperature constant, let's say keep it on a stove that has 100 degrees or something like that, in contact with something that consistently keeps it at the same temperature. I can play with the change in volume and pressure and so on. So you come up with this ideal gas law. I'll just give you a summary. Pressure times volume is equal to the number of moles and times R, this ideal gas constant, times the temperature T. Now we're going to be working in SI units. SI units, meaning the pressure, P is pressure, and it's measured in what? What's the SI unit? Force per unit of area, right? Pressure. So it's newtons per square meter or a Pascal? Yeah. It's in pascals, PA, pascals, newtons per square meter. The volume, what are the units of volume in SI units? Cubic meters, meters cubed, yeah. I know in chemistry you probably worked with liters also.
Yeah.
That's fine, but you would have different gas constant in that case. So we will work with SI units. So this one is the volume. We will just always use cubic meters. Okay? N is the number of moles. And then R is the gas constant. I'll leave it last. The temperature is, T is the temperature. Now what should we use? Kelvin. Yes, you have to use the Kelvin. You have to use Kelvin. Yeah. And we'll see that if the temperature goes to 0, if you're using degrees Celsius, 0 degrees Celsius, the pressure is not 0 at 0 degrees Celsius. But at 0 K, in principle, in classical physics, the motion would stop and pressure should be 0. Yeah. So, yeah, you have to use K. Don't use degrees Celsius in the ideal gas law. Now, R is this universal ideal gas law constant. It's called, I forget what the exact name was. Yeah, the universal gas constant. Universal gas constant, and it's about 8.31 gas. I'll just call it gas constant. And it's 8.31 joules per mole Kelvin. 8.31, yes. So you can take the ideal gas law to be just, it's a relationship between all these variables. Pressure, volume, number of moles, and temperature. So the ideal gas law is constant. The ideal gas constant is a constant. The number of moles may be constant. If I have a piston and I trap my atoms in a container, the number of atoms will be constant, right? It's not changing. If you have the gas leaking, then yeah, the number of atoms will be decreasing. Or if I pump some gas in, the number of atoms will increase. But usually N is constant also, right? things that change will usually be the pressure, the volume, and the temperature. Alright, so let's take a look at an example here. And let's say, it says here, suppose you have 100 grams of oxygen gas. We did this example earlier, 100 grams of oxygen gas. And we figured that the number of moles was, I think, 3.13. We did 100 over 32, gave us 3.13. So suppose you have 100 grams of oxygen gas, and it's placed in a volume of, it occupies a volume of 600 cubic centimeters. So that's probably the last example. So example here. 100 grams of O2 in a volume E equal to 600 cubic centimeters. Right? Cubic centimeters. And the question is, what is the pressure when the temperature is 150 degrees Celsius? So find P when T is equal to 150 degrees Celsius. You hear gas and you should probably want the ideal gas law. Yeah, so that's what you want. So we know that PV is equal to NR times T. R is a constant, it's 8.31. The volume is given, the number of moles is given indirectly. And it's, yeah, we did it earlier, we found that the number of moles was 3.13. So here's what we know. We know that the volume is 600 centimeters cubed. We need to change it to what? Cubic meters. So each meter has 100 centimeters. So we have to divide by 100 3 times. Because it's centimeters cubed means it's a centimeter times a centimeter times a centimeter. So I have to convert to meters 3 times. So each time I have to divide by 100. So I have to divide by 1,000,000, right? Because I'm dividing by 100 3 times. So I divide by 1,000,000. So that gives me 600 times 10 to the minus 6, which is 6 times 10 to the minus 4. Good. So 6 times 10 to the minus 4 cubic meters. That's the volume. All right, that's good to go. I need this. Number of moles we said was about 3.13. R is given, it's 8.31. The temperature I need to, can I work with 150 or I need something else? So you need to change to what? To Kelvin. So you need to add 273. So what do we get here? 300, 423? 423K, right? So that gives me the pressure to be nRT over V. So plug in the numbers. 3.13, 8.31, 423, and the volume 6 times 10 to the minus 4. That would be a large pressure, right? Huh? Large, yeah, 18 something you said? Yeah, I will just, it says I have 1.83 times 10 to the 7. Yeah, thank you. Pascals, right? Or newtons per square meter. Okay. So, I was going to do one more example, but it's 12:45 or 35. Okay, so I should be quiet now. All right. So I'll see you. I have a class right now. Some of you will see me in 10 minutes. So others, I will see you tomorrow. Right? I'll try to post these today.
Thanks for